我们的节目经常有我跟著名科学家的对话。最近我参加了科学家请回答2021的系列对谈活动，世界顶尖科学家协会与今日头条帮我联系到了一位诺贝尔奖得主巴里什，他和另外2位科学家雷纳韦斯和基普索恩因为探测到引力波获得了2016年的诺贝尔物理学奖。实际上我以前就见过他们。2017年12月18日，中国科学技术大学上海研究院举办了一场引力波大会，邀请这3位诺贝尔奖得主演讲，潘建伟做主持人。当时我就在现场，后来把这次经历写成了一篇文章，听3位诺贝尔奖得主讲引力波。不过当时我并没有提问，因为我觉得这样的机会最好留给公众，专业的科学家有的是机会交流。果不其然，4年后，在第4届世界顶尖科学家论坛即将召开之际，我要和巴里什教授进行一次深入的对谈。4年来，引力波科学取得了很多新进展，但大多数公众对这个领域仍然感到很神秘。下面我们就来和巴里什教授连线。
Hello, nice to meet you.
Nice to meet you. I can hear you very clearly. Thank you.
And I look forward to the talk. What is the big background behind you with all the lights? What's behind you?
The background. Actually, this is our center. We have made a center of science communication research that is held by the CAS, Chinese Academy of Sciences. This is a new institution, and I am one of the vice deans of this science communication center. So this can reflect that we think that science communication is very important. So this is for the background of our interview.
Good. Well, I think it's important.
Mm-hmm.
Science communication is important, so I agree.
Thank you. So, dear Professor Barish, I'm very delighted to see you again. It is again because in December of 2017, I had listened to the speeches of you 3 in the form of gravitational waves held by the Emission Salon in Shanghai. Do you remember that forum?
Yes, I do. Yeah, I do.
Yes.
I remember. I had just come from Sweden to Shanghai at that moment, and when I arrived in Shanghai, my suitcase with my clothes didn't arrive. So when you saw me, I had gone to the department store and bought a jacket, which happened to be the jacket I have on right now.
So that was a very interesting forum. And after attending that forum of gravitational waves, I wrote an article of science popularization. So I explained gravitational waves like this. So all the motions of matters happen in the space. The matters are like actors, and the space-time like the stage where the actors play. The normal waves like water wave, sound wave, and electromagnetic wave are such that the actors are moving, but the stage is still. Why the gravitational wave is different from all of them? It is the motion of the stage itself. Therefore, it is often compared to the ripple of space-time. So how do you think about this description? How would you introduce gravitational wave to the general audience?
Well, I think that's a nice pictorial description. It catches the right difference, which is that it's the stage rather than the actors. It misses a couple of points, though, that are very important. It misses the fact that when the stage moves, it moves very fast. It moves at the speed of light. It doesn't just move. The stage doesn't just move. It's moving very, very fast. It moves at the speed of light. And the second is, if I were giving a description, I might give that description, but also I have to tell them that it goes at the speed of light. And the second is that any curious person wonders what makes the stage move.
Yes.
Okay. And so that also should be in the explanation. And what makes it move? General relativity is that it's caused by any acceleration of masses. If you have a mass and it accelerates, not moves constant velocity, but accelerates, then it emits gravitational. So gravitational waves are made by accelerating masses, and they move at the speed of light, and then they act just like the stage moving as you described. So I would add those 2 things when you do it next time.
Yes. So
it should be stressed that not all the motions by massive matters that can produce gravitational waves. There are some motions which do not generate the gravitational waves, right?
Yeah, it requires an acceleration. And there's accelerations for when it's what causes gravity in general. There's accelerations for moving objects, like the moon going around the Earth, gravity pulls on them. And so it takes an acceleration. Mass is not staying in the same place, but having acceleration.
Yes,
so that's what
so motions like this can generate gravitational waves, but like this, you will not generate gravitational waves.
Right.
So actually, all the motions we observe will generate gravitational waves, but most of them we cannot detect the signals because they are just too small, right?
Yeah. So the words that are usually used are the gravitational waves cause a force. The force of gravity explain the force of gravity, and so gravitational waves have to come about from some motion that gives this effect. But we're lucky because the stage doesn't change shape very much. Gravitational waves distort, Einstein's famous words, distort space and time. And so if we think of why the apple falls to the earth, Newton told us the apple falls to the earth, and he gave us an equation that it's inversely proportional to how far it is from the earth and a product of the masses, how far it is squared and the product of the masses. But in effect, the force of the gravitational effect, the distortion of space-time is actually very small. And that means that when gravitational waves cause a distortion of space and time, or a distortion of the moving of the stage, it doesn't distort it very much. You might think of it like a material, like a bar of steel or something. It's very stiff. We're fortunate that space happens to act like a very stiff material, because otherwise everything would be distorted by general relativity, but it's very tiny. So we're lucky as people that we live in something where the properties of space are very stiff, but it makes the problem of seeing gravitational waves very hard for somebody like me. So there's two sides.
Yes. You said the bars. That reminds me of the Weber bars, right? That's the first apparatus to detect gravitational waves by Weber, but he didn't find that. But he thought he did find that.
Yeah, he thought he did, but unfortunately, he was a very clever person. He really started this field, and he had a lot of clever technical ideas. But unfortunately, I have to be critical of him as a scientist, because as a scientist, one of the most important ingredients is to be skeptical, to have to prove that something is right. And he wanted to detect gravitational waves. He wanted to believe in it. And unfortunately, that kept him from being as critical as he might have been.
Yeah. And I think there's another question for the curious people. They would ask, what is oscillating? So what property is oscillating?
Gravitational waves are like a wave. It goes up and down, up and down, up and down. And in one orientation, when it's up, it distorts space one direction. And when it's down, it distorts space in the other direction. And so it goes back and forth between distorting space in the two directions.
Yes.
America, we have in an amusement park, you sometimes go and they have a mirror, and you go and stand in front of the mirror, and it makes you look tall. And then you go to the next mirror, and it makes you look short and fat.
We have this mirror too. Yes. This is a funny mirror.
So gravitational waves have the effect of basically having you go back and forth between the two mirrors. You get a little taller, you get a little shorter and fatter, and back and forth. And the speed at which you go back and forth is the frequency of depends on the frequency of the gravitational wave. So it could be, 100 times a second, it could be 2 times a second, it could be 1,000 times a second, and different physical phenomena that create gravitational waves will give different speed at which you have to go back and forth. And that helps us understand the object that made the gravitational wave.
Yes. So when there is a gravitational waves, you are stressed in one direction, but compressed in the other, right?
Yes. Yeah. Until half a wavelength later, you go the other way. You get squashed. And then you go back and forth.
Yes, yes. So generally, the area doesn't change, right?
No, the area is the same.
So should we say that is the curvature of the space-time that is changing?
Yeah, it's because everything I described was like two-dimensional, but in real life, it's actually four-dimensional. It's not. It's the distortion is in three-dimensional space and time together. Einstein made the collection of four-dimensional space and time together. He made one word, space-time, in German, but in English, we write it as space-time. Our word processor, when we type it in on the computer, draws a little wavy line under it, like we misspelled it, but it's right. It's one word, space-time, and it's four-dimensional. So
yes. It's three dimension of space plus one dimension of time, but altogether it's mixed up. They cannot be.
It's all mixed up and it's very hard to visualize for that reason.
Yeah. So the next question is for the general audience. So how would the gravitational waves influence our future? For example, something that in the long run it would only stay at the level of fundamental research, not make much difference to our real life. So what is your opinion?
That's a question that I have strong feelings about, and we get asked. My life is doing fundamental physics, so our fundamental research, and so it's really the value of fundamental research. When we do the research, we don't ask ourselves what it can be used for later. We do it to understand nature. However, it has turned out that understanding nature has been a very good way to develop very important devices, very important impacts on society. And you may not even have understood that when the science was done. So we don't know for gravitational waves whether it'll be useful. All fundamental physics doesn't end up being useful. But I'll give an example. Another example from Einstein that to me is a wonderful example of how fundamental science can pay off. Einstein in 1919 proposed something else, not gravitational waves, but something which he called spontaneous emission. And that was a nuclear physics effect. That was a nuclear physics effect that was just an effect. The experiments that were done on it to prove that it was a real effect were done in when I was a student in the late 1950s in Berkeley and at Hughes Aircraft. This spontaneous emission. Spontaneous emission has the effect that it's like a chain reaction. If you excite one, it excites another, and they're correlated. It was not at all understood that had an application at that time. About 10 years later, in the late 60s, actually, the people started recognizing that you could make a device that had a very focused beam because of this coherence. And as you said, you guessed right ahead, that was the laser. So the laser came after a fundamental discovery. And the word laser, I don't know if you know that, the acronym laser means light, amplified, spontaneous is the S, emission, radiation. So the word spontaneous emission is in the letters of the word laser, and that's where the word laser came from. It's now, for people who like economics, it's about a $30 billion a year industry that wasn't even understood that it made anything useful when it was made. And it came out of fundamental physics. I'll mention a second one just to show that that's not a complete accident. And the second one I'll mention was another effect that I followed in my career, which is called nuclear magnetic resonance. Nuclear magnetic resonance was theoretically discovered soon after World War II. It was Purcell. It was discovered in Cambridge, Massachusetts. And then it was pursued in different ways, and variants of it have been done afterwards. It was more than 20 years later that people realized that using this principle, nuclear magnetic resonance, we can make an imaging device for medicine. And that imaging device, which in our country at least is called MRI, magnetic resonance imaging, is the most precise imaging device we have in medicine today. It's called MRI because people don't like the word nuclear.
Right. People are afraid of nuclear.
Yeah, but in fact, it is that exact effect imaged and is our best. And both of those came from what were absolutely curiosity-driven experiments, just like gravitational waves. Now, everything we learn in fundamental physics isn't necessarily going to give an application, but I didn't give the only two. If you do basic research instead of just trying to apply things, that we should have learned by now that it easily pays for itself. Not each experiment, not each discovery, but the fact that moving our knowledge forward gives us in undesigned ways completely new ways to do things. And certainly the laser and the MRI are two wonderful examples of modern physics giving a very nice payoff for society.